Now I want to start bringing in the idea of the generalized linear regression model. So what have we got going on here? So let's look at our model that we've had experience with, so we can have as many explanatory variables over here on the right. So I indexes the particular observation, so you can think of that as a row in your Excel spreadsheet, and these are the various covariates or explanatory variables that we have, and we have sitting on the end here an error term. So our dependent variable can be explained by some covariates, and then we have this error variable on the end. Now we know that there are some assumptions that are sitting behind this. The first one is this: the expected value of y, okay, can be explained by these covariates. That says that we can actually model the variable, so it says that we haven't got any omitted variables in our model, or there's nothing structural missing from our model. And if there's nothing structural missing from our model, it means that it's safe to have this assumption that the expected value of the error term is 0. So we really, if we haven't got truth in this assumption here, that there's we can explain what's going on average in the dependent variable by this functional relationship, we've got a problem. We also have this assumption of homoscedasticity, which is the assumption of equal error variance. We also have the assumption that there is no correlation between the error terms. So here is I and j index any two error terms, and that we expect the covariance of this thing to be 0. And this here is the expected value here. There's no correlation between an explanatory variable and the error term. That's a little bit of more of a technical one, and depending on what kind of modelling you're doing, this may or may not be a problem. The more experimental you are, the less likely this one is to be a problem, and the more observational you are in the way that you collect your data, the more likely this one is to be a problem. And for inference, we can either rely on the central limit theorem, or we can make some assumption about the error term. And if this thing is normally distributed, it technically means it can run from negative infinity to positive infinity. Now, often you would have been aware we might have been measuring continuous variables which clearly could not have taken negative values. So, for example, the diameter of a tree. But it doesn't matter. It's enough of an approximation for us to work with. So that's what's sitting there in the background. Now this generally works okay for us, but we run into some problems if we have 0, 1 data. Now for us, where are we likely to come across 0, 1 data? I think it's primarily in a natural resource management context about things about asking what people would be willing to pay for something. So this is something where we might want to do some restoration work. We go out and we survey people and we ask them the question, are you willing to pay some amount to achieve this restoration project? And they either answer yes or no. And then we code this data as 0 or 1. Okay, so when we've got 0 or 1 data, we're going to have some problems in relying on the standard linear model. So what does it look like? So here's my continuous variable here, say price. This is, the price, are you willing to pay to achieve this restoration outcome? I've asked people different prices. People that say yes, I've coded as 1. People that say no, I've coded as 0. All right, and that's, if we try to visualize the data, what it's going to look like. Now, we know that we're going to run into some problems, but we could still model this. So we have y, this is our 0 or 1, is equal to an intercept and a slope term, okay? And here the x is our price. Now, if you were to estimate this model, it has an interpretation in probabilities, and so some people often call this a linear probability model. All right, so what would this look like if we were to fit this kind of model to the data? So it would look something like that. Now, hopefully you probably think that doesn't seem like a great fit to the data, right? So we've got some data up here, some data up there, and this linear probability model is just going to whack a line somewhere in between them. It's upward sloping, which I guess is what we would expect. As the price that we've asked people to pay has gone up, people are less willing to say yes, maybe, not sure. Okay, so this is what kind of setup we've got. Now, what about if I extend it a bit further? So now I've just taken this slide and I've simulated some more data and I've really drawn it out. So you can see out here, the predicted values go beyond 1 or 0. Now, if you're talking about a linear probability model, that's a bit of a problem because probabilities are bounded by 0 and 1. So it's a little bit of a problem that the model would be predicting values beyond 0 and 1. You can't have a negative probability and you can't have a probability above 1. So our model's got some flaws. We've also got some other problems with our model. So y can either be 1 or 0. All right, so it means the error term must either be 1 minus p or minus p to make this thing balance. Okay, so that doesn't look like a continuous variable. We've got our error term can only take this value, 1 minus pi, or this guy down here. Now that's going to give us heteroscedasticity. Sure, we know we can deal with heteroscedasticity, but it's a little bit unsatisfactory to be saying, well, we know what we've got a problem here and we're not going to do anything about it. So I'm going to give you a motivation for this model, my first attempt at motivating this model, which is really driven by this idea that we don't like values outside 0 or 1. So let's go. Probabilities are in the range 0 to 1. Okay, so we want to be modeling a probability. Let's say that we want to model a probability. So we've coded our data, yes equals 1, no equals 0. Now we want to model it as a probability. So we need to be on the scale 0 to 1 rather than 0 or 1. Now, one thing that we know, odds are probability divided by 1 minus the probability. So that's the odds in an event. You know, we really see this in horse racing so much, but we can move from probabilities to odds via a formula. Now, if the probability of an event is 0, then this formula collapses to 0. If the probability of an event is 1, then the odds of the event are infinity. So what you can see here is that rather than being on the 0-1 scale, by saying I want to model this as if it's a probability, and I put it on the odds scale, I'm now going from 0 to infinity. And that looks like something that is, you know, sort of halfway towards the kinds of things that we modeled. Theoretically, we were modeling things that can run from negative infinity to positive infinity. Now, the next thing we can do is think about what we know about logs. Okay, so for any number less than 1, the log of that number is a negative. And it will get, as it gets smaller, it will tend to negative infinity. However, the log of infinity is still infinity. Okay, so now if we take the log of the odds, technically this expression can run from negative infinity to infinity. So we call this expression the logit, and the logit runs from negative infinity to positive infinity. What is the logit? The logit is the log of the odds. What are the odds? The odds is just the ratio of the probability divided by 1 minus the probability. And that's something that we know what to do. Now, this expression, like a log odds ratio, is something that doesn't have very much of an intuitive understanding. But what we can do is, when we want to go to understanding what these expressions mean, we just undo the step. So we can take the anti-log to get the odds, and then we can convert odds to probabilities because we know that formula. And so we can undo all of the steps that we do. Okay, so that's one motivation for saying what we're going to model is what we call the log odds ratio. My second motivation is something like this. Right, suppose the probability of the event changes smoothly in response to an x variable, and that's really what we're saying in our model, that there's a relationship between the explanatory variable and the dependent variable. And let's say that our dependent variable is a probability. So we have a probability, and if we're talking in probabilities, we want to constrain the function so that it stays between 0 and 1. Now, if you start thinking about that, then we need something that's smooth. Well, an S shape will give us that smooth shape. So an S shape going like that, right? So we're going to have a nice smooth S shape. So we know something about how to get an S-shaped curve. In fact, this formula here will give us an S-shaped curve. And I guess I'm just showing you that you can write this in a number of ways. So I want to say that the probability of y, the probability that y equals 1, responds to x via a smooth S-shaped curve. And if I use this relationship here, then that's going to give me that S-shaped curve. I can also do some rearranging, and I can sort of clean up my notation a bit. I don't, you often see it written like this, but it's okay to write it out in longhand like this as well. Now the trick with that is that we want to have the expressions on the right hand side as in a clean form. So what we're going to do is we're going to have to say, well, I've got this expression on the right hand side. What I'm going to need to do is I'm going to need to transform what I've got on the left hand side so that I can get this part here on a nice clean expression on a linear scale that we might be able to estimate. Now, so if you work out the transformations on this to get that part down the bottom, you end up with the expression that we've got down here, which is the log odds ratio and our linear predictor over on this side. So we're saying this is going to be giving us the change on this. And how did we end up in this? Because we wanted to change or constrain the probability to be in the 0, 1 space, we picked a simple S-shaped curve, and that's what we get up with. So we got this model that the log odds is related to these linear predictors, and that's what we can work with. So let's just see if we can understand what's going on here a little bit and see where that gets us. So let's not worry about so much, really deriving this, but let's take a heuristic approach here, and let's say, well, let me pick some values for the intercept and the slope and see what sort of shapes we get in our curve. And that's what I've done here. So my first curve here, I've got an intercept value and a slope of minus 0.1. Okay, so what you can see is if I change the slope to 0.2, we get this steeper curve, this steeper transition from 0 to 1s. You can see it's constrained by 0 and 1. If I really crank up that slope to 0.8, you can see it snaps. The curve is, basically going, there's a really sharp transition from being in the 0 space to being in the 1 space. So with this parameter, we can get the full spectrum of slopes from something that's really, really flat to something that's really, really steep. And then with this variable here, what we're doing is we're shifting. So if I change the slope, you can see it shifts where I cut the 50% point. So I can move my curve around with one parameter, and I can change the shape of my parameter here. So this is really what we need to know. Yes, this is going to constrain us to be within 0 and 1. Very simple. And because it's related to those linear predictors, we can estimate this sort of model. The final thing that I'm going to just introduce you to here, there's a couple of related things around this point about the way the slope behaves. So a special point about this, if we solve this curve, is that the ratio negative the intercept divided by the slope is the value when the probability is 0.5. So 0.5 is a key value. That's sort of the switching value, or something in a policy setting where we might think that's 0.5 plus 1 is the point of majority support. So if we just plug in those ratio values, we can see that it drops out at a half. So that's an important thing, this ratio here, the negative of the intercept divided by the slope. All right, and you can find this if you take this function and you do some calculus, and you can do all sorts of interesting things to find this. I just find it's easier to demonstrate by plugging in the values. Actually, the calculus is a little bit tricky. Okay, but we've seen it, right? We've plugged in the numbers, and we now know that that's true. The other thing about this curve is the marginal effect, and that's sort of what's happening here is, so if this is our slope, so our slope is actually non-constant, okay? So when either of these two expressions get very small, and that could be if p is close to 0, this thing will collapse, and if p is close to 1, then this thing gets close to 0, so this whole thing collapses to something close to 0. So when we're near 0 or 1, slope, which defines the marginal impact, is very, very modest. And it's also going to hit its maximum impact at the point where it's 0.5, the probability is 0.5. So just by looking at that, and we know we constrained this thing to be an S shape, right? It's an S shape, which means that the marginal impact at the tails is going to be quite modest. So again, I've just plugged in some values in here. So if the probability is 0.1, you plug it into the formula and you can see that's going to be whatever our B1 is, it's going to have a smaller marginal impact, okay? Because it's going to be multiplied by this. We get into the middle, you can see that it peaks in the middle here. So the marginal effect is most strong, right around a 0.5 probability, and then it declines. And in fact, this particular S shape, it's symmetric. Now there would be a whole bunch of different S-shaped curves that you could fit. They all work pretty much the same, so we just pick the simplest one we can. So that's really an overview of the theoretical properties that we've got here, and that's an opportune time for a break.